Rubin never uses computers.
Okay.
Things.
So
amazing that he's contributed so well to Gibbs, which is so computing oriented, and he can still do it.
Yeah.
Yes, as a teaser here for you now to take interest in what this man says during your last 10 minutes of energy. When you have like 5 different data sets imputed, you get 5 chi-squares. Your natural naive instinct is to take the average of those 5 chi-squares and use that as an indication of how good the model is. That's bad. And it is giving you a false impression of the model fitting poorly. When you do it the right way, the model will fit better.
Yep. All right, so just show a little bit of... okay, so here's Rubin's beautiful formulas, right? So again, as Ben said, likelihood ratio test we denoting by TM. For the mth imputed data set, we just compute the chi-square test. Q0m, these are the estimates for the H0 model. Q1m are the estimates for the H1 model. This is sort of the naive curve, which is again the sum. You just average these chi-square values across the imputed data sets. So T bar, and then these are the average parameter estimates for the H0 model, and these are the average parameter estimates for the H1 model. This is basically is going to explain how Rubin's method works, and you don't need to know this really. Trust them, we're just telling you this so you know what Mplus does.
Can I interrupt for a technical adjustment here? More of that.
Yeah.
You now correct your corrected handout with technical. Listed on the Mplus website later on. But for now, note that your handout does not have a prime up there, and it should have. It does have this bar, but it should have bar. Should. Corrections. The interest formulas should be made.
And yeah, the formulas are again in that. There's a separate note on this, on the website that actually goes through this exact simulation and goes through this.
It's under technical appendices.
Right. It's not part of the imputation, multiple imputation note. It's in a separate note. Okay, I'll flip this. And basically, let's see. What is this now? We generate 20% of the data is missing. This is the sample size, 100, 500, 1,000. And we basically compare the 2 chi-squares. This is basically the naive version. It's just using the average. And this is the correct version of Rubin's formula. And you have 8 degrees of freedom. And you should expect an average value of 8. Instead, you get much higher values here. And here in this particular simulation, the true model is correct. Excuse me, the analyzed model, the model that we analyze is the same as the true model. So if you want to reject the model, instead we get 5% rate, exactly rejecting the correct model. The Rubin's chi-square actually rejects 5%, which is the nominal rate that it's supposed to reject. And if you actually get more missing data into the simulation, the results are even worse. It was nearly 100% rejection rate. Rubin's formula actually produces values.
So the naive chi-square is 2 to 3 times too large.
And I think the factor that it could be large as you want. In a simulation study, you can make it as large as you want. Okay, and finally, this is our final slide.
Finally.
Yeah. This is our final slide. And basically what we wanted to know with this simulation study is this new chi-square powerful enough? Because it doesn't reject, right? On the previous slide, we saw that it doesn't reject as much. So we just wanted to make sure that it's still powerful enough to be useful. And we basically compare this method against the full information analysis of the missing data. So you have some missing data and nothing else. You don't have anything else. You have two ways of analyzing it. You can impute the missing data points, or you can use FIMO to analyze it. And this way you can compare, you can actually compare basically. So the way you do that is you simulate data according to one model, but you analyze it according to the wrong model. And you get so the power of this chi-square statistics is actually is fine. And the reason you actually get this, loss a little bit. Anybody wants to guess why you get that loss of power? Anybody still sharp enough to figure this on the moment? Okay, we've thought about it for days to figure it out. So anyway, from our restricted model, not as accurate as if you impute it from the restricted model, then the power would be like here. But here we actually impute it from an unrestricted model, saturated model, which is less accurate. It's not going to give you the same precision as.
It blunts the misspecification.
Yes, it blunts the misspecification. Exactly. So I think that's it, I guess.
Well, that's pretty good stuff.
Yeah.
You know, we wanted to give you tidbits of what you can do in Mplus now, but we also wanted to give you ideas because there are a lot and sandbox to play around with that hasn't been touched. But do it at your own peril and be careful. And send us only your successes. But finally, we wanted the organizers thank them, Betsy and her husband videotaping us. Betsy, thank you very much. And thank you, Tiermer, for your first time teaching. I think you did well. And we do want to give you a chance for questions and answers, but first Betsy has an announcement.
Yeah, before people start leaving, I just want to let you know that tomorrow's session is not in this room. It's actually in Castleman 212, which is the next building over. We actually had so many people register for the conference that we outgrew this room for tomorrow. So we'll be using Castleman 212, and Castleman is the building right next door to this one. If you followed my direction to go to the Student Union for lunch today, it's the building that you passed on your left, the very next building. I don't know what direction that is. I'm bad with directions, but this way. Is it west? I would have said north. So coffee and continental breakfast and registration will be there. That starts at 7:30, but also note that because you read the pre-conference for continental breakfast starting at 7:30, but if you want to sleep in a little longer, the conference doesn't start till 8:30, and you just need to get there in enough time to grab your coffee and your bagel.
And the first talk starts at which time?
The first talk well, the welcome starts at 8:30, and the first talk starts at 8:45 tomorrow morning in Castleman 212. And that's you, right?
Again?
Again! That's right.
Oh boy. Name again?
categorical variables in multiple imputations. My understanding is that there's a little bit of controversy about that in terms of you multiply categorical variable values, or you should just leave them at whatever the predicted value is for that variable. And just tell me what you're doing.
Yeah, so the question is, with categorical outcomes, should you impute an integer corresponding to what the observed data is, or should you allow for the in-between values, say the underlying continuous response value even?
Or actually, I think what some people might be doing is if you actually regression, you ignore the binary, you get value, say, 0 and 7. Instead of 0 or 1, you get a value of 0.7. Not even the underlying. So yeah, I mean, that's not what we do. Basically, we impute the underlying normal variable, look at the thresholds, if it's a threshold, it's 1. If it's we don't get bias. I don't think this, it doesn't show bias.
You want to say something on that, Dan?
Yeah, I can't remember the paper now, but Enders talks about this in his book.
Mm-hmm.
And there has been a paper that showed bias in some applications.
Yeah.
And what they did instead was look at the distribution around the mean, and they sort of shrunk it.
But theoretically speaking, there is no bias. There's no. Where do you break the theory? Here, there's no. I mean, I don't see how you can get bias. I don't know.
I've seen that literature, but it's something that I'd like to study further before I try to answer your question.
Is the imputation done from this, variance covariance model? Because if it's done from this model, theoretically speaking, you can't get bias. If it's for small sample size, maybe some.
It's not bias. It's the truncation is the bias. It's not bias.
The best value may not be 0, but 0.1.
Right, or 0.9 or 0.8, rather than
Predicted value.
Yeah, using the predicted value, and the fact that you're moving it depending on whether it falls above or below 0.5.
We'll take a look at take a look at it and give you an answer next time.
Yeah. But you see, we even present a lot of simulations. There are a lot of simulations on the website. Theoretically, this is really solid. There should not be bias unless something else is going on.
Yeah,
but
there may be
these
other
matters that
aspects
present here.
Yeah.
I can't explain it.
Okay. Well, there's a lot of research topics here. So, yes.
I think Anders made a strong case for using more interpolations, like 20 or more.
Rather than 5, you mean?
Yeah, I think in terms of power.
He did say 20.
I guess it depends on the percentage missingness.
Probably, yeah.
Yeah.
There's no real reason to use it with computers being so fast. You don't lose anything from the computing time by increasing the
Sure.
using power. So
Sure. Yeah.
20 or above is also a good rule of thumb.
Yeah.
But our experience is also, so far I'm yet to find a case where it's needing more than 5. And, it's kind of, again, very surprising that Rubin actually guessed this number without using any computers, right?
Well, he did something on the back of an envelope,
Okay.
I think. Yes, Dan.
But more imputations may affect the difference in your test for fit as well.
I think
The
actually,
difference between Femmel and
yeah, I think here we actually used 50. Wasn't this where we used 50 and 5? I can't remember now.
oh, so you've looked at that.
I
Can't remember.
I think theoretically, right, the larger the number of imputations, the closer it should be to the map.
yes, that's right. Yeah.
That would support the comment.
More questions? Yes.
One quick question. Does the Monte Carlo utility in Mplus, can it be used to do like power analysis for Bayesian?
Can the Monte Carlo feature of Mplus be used to do power analysis of Bayesian analysis, is the question. How would you answer that?
Yes, that's I do this every day, non-stop, sort of. So, that's how we do. I mean, every algorithm we check with Monte Carlo in simulations. So, yeah, yes, Bayesian, Monte Carlo, yes, that's.
Yes, Levent?
Factor score estimates are not available when we are fitting factor mixture model. How about plausible values?
Factor scores are available with factor mixtures.
Are you referring to EAP estimates? Or?
We have them. We give them both for most likely class and the mixture over the classes. Or maybe you're thinking about something else.
Let's say we have two-factor model.
Mm-hmm.
So the C is 2, and they are different one way or another. You don't get factor score estimate specific to each class. What you are referring to is the
most likely class.
conditional global.
We get it for the most likely class.
Yeah.
Yes. We get the factor score for the most likely class, and then the mixed.
But
But you want it.
class membership, not latent trait estimate.
No, latent trait too. Yes. And I think we and plausible values.
Can you use
Yeah.
latent trait estimate?
Yes.
Yes.
Yeah.
I've used them, so I know.
Yeah, the only limitation in the ML stuff is basically in terms of being able to compute standard errors. So in some cases you don't get standard errors. In basic you always get standard errors. It's just very easy, right? For us it's just to compute the sample variance of the...
For factor mixture models, we get class-specific continuous latent trait estimate.
Yes, we do. Yeah.
Like,
Yep.
Yeah.
you have to time out to the
Oh, no, just you type save equals factor scores. That's all you have to say.
How about
Save equals
how
FS.
about if we use
Plausible values.
can we also get the plausible value?
Yes. Yeah.
And it's the same thing, right? For the most likely class and for the mixture, or how?
Well,
actually, that I
what
don't know.
you have to keep in mind that what you're going to get is the C value, imputed C value,
The
as
latent
well
class membership.
as the class membership, as well as your factor score. And if you want, you can pile them up. Say what's the average in class 1, what's the average in class 0. So you get different. You can get even for people that flip classes, that that they're not categorically in one or the other class, you can get factor score estimate in each class with base.
More questions? Yes.
And auxiliary variables be categorical when they do play a role in the conversation. In a FAMO.
Are you thinking in the ML context?
Yeah.
So you have the auxiliary M feature, and you bring them into the model, and you're asking, can they be categorical? We only allow it for continuous, right?
They'll be treated as continuous. So it's not. This auxiliary command is not available for weighted least squares. Weighted least squares is a little weak when it comes to missing data. So it's developed just for ML. The original article is just for maximum.
So in that regard, the Bayesian approach, where you explicitly designate it as categorical, would be more exact, I think.
Yeah.
Yes.
So when you have a categorical variable in this computation, which prior distribution are you using for those variables?
Sorry, can you say again the question?
For categorical variables, which prior distribution are you using?
For estimating of which model?
For the imputation model.
Okay, so basically we do anything to do with categorical variables. We uses weakly informative priors. What that means is basically if you have some kind of a regression, probit regression slope, it's going to be normal 0 with variance 5. So it's actually going to be something with a shape. It's the real thing. It's a real prior. It's not very sharp, but it's a prior. So you can modify that if you think it's too restrictive or too wide or too. But that's what we figure out that this works really well in general. If you don't want to think about it, just use our defaults. It's also for the variance covariance matrices and the correlation matrices. We do use the inverse Wishart with the identity matrix and P+1 degrees of freedom, which basically is the one that gives you uniform on the correlation. So the correlation, the marginal for the correlation will become uniform on -1 to 1.
And the thresholds are normal.
The thresholds are actually, 0 to infinity. We've never had any problems with the thresholds, actually. So
it's just pretty nicely uninformative, yeah. Well, who's going to ask the last question? Well, we'll be sitting here for a while, won't we? Well, Ken has a question.
The bank was gracious thanking everybody else, but I think we should thank him as well.
And thank you. All right. Thank you, folks. You were a great group. Go out and do good analyses. And how many are now thinking maybe Bayes could have some value? All right. Good.